Well, howdy there, Internet students. It's Mr. Hermanson again. Hey, you guys, today you're going to learn about a thing called Pythagorean's theorem, one of the most famous math theorems there is. And it's actually probably something that your parents remember and and use. It's been around since sometime in BC, a long, long time, and it's very, very useful. Okay, for people that are carpenters, for people that are tailors, for people that are bricklayers, for anybody that works with distances or needing to make things with right angles. They use Pythagorean's theorem. So you need to discover this for yourself, otherwise you won't really remember it. So, so that's what we're going to do right here. So let's try this right now, you guys. We want to find the exact area of this square. To do that, you basically just need to add up how many squares fit inside it. See how close you can come, and then I'm going to show you a pretty cool way of doing that. All right, so what I do to find this area is I split it up into shapes that I can easily find the area of. And I'm going to use triangles and squares. Um, I'm going to actually try and make the same size triangles here. So those two are the same size triangle. That one's the same. And that one's the same. So there's four of those triangles plus one square in the middle. Now to find the area of a triangle, you take base times height divided by 2. And you should be able to tell that the base of this triangle right here is 3. The height is 2. 3 times 2 is 6. Divided by 2 is 3. So there's 3 squares in there, 3 squares in there, 3 squares in there. And if you add it all up, you get 13 square units. And so now that we know the area of that square, we could actually find the side length of the square. The length of this, remember that the side times the side of a square equals the area, so s squared equals 13. We're going to undo that using the square root. S equals the square root of 13, which is about, I think it's about 3.6. You can check me on that, but it's exactly the square root of 13. All right. So that kind of process we're going to need today to help us discover Pythagorean's theorem. All right. One thing you need to know about right triangles is the different parts have names. The two sides of a right triangle are called the legs, the two sides that make the right angle. And then the longest side is called the hypotenuse. Now this is for right triangles. And this relationship is for right triangles. All right, so you tell the legs of the hypotenuse because they make the right angle. And then the other side we call the hypotenuse. You might have to say that a couple times to the point where you can say it. All right, you guys, we're going to discover Pythagorean's theorem by doing this little model here. We are going to do for each of these right triangles here, and you see the fuchsia colored triangle right in there. We are going to do we're going to draw areas on each of the sides and find the areas of those squares. Now you're going to have to use that trick with the triangles to help you do the third square. I'll do the first one for you. So this, the area of the square on side A here, this area is 4, and you can tell that just by counting 1, 2, 3, 4, or doing 2 times 2 on the side lengths. So that's exercise number 1, side A. The area of the square, so we're doing areas here, is 4. Okay, now side B, this is a 3 by 3 square, right? So that would be 9 units there. 3 times 3 is 9. Side C, we got to use my little trick. Actually, here's how it works. And you can do a little diagram kind of like that, split it into 4 triangles on all these when you need to. But anyway, so each of these, this is 1, 2, 3 on the bottom and 2 high. 3 times 2 is 6. Divided by 2 is 3. So these are each 3. hey, this is the same square that we just did on the other page. There's one in the middle, so that's 13. All right, so I'm going to pause here. You go ahead and find the areas of the squares on the other 3 triangles and fill in the chart. All right, so here's the numbers I got. You can check here, see if you got them all right. And that's how I split them up so I could count them. Okay, so we want to look for a pattern in this table, and for the cases you considered, what is the relationship among the areas of the 3 squares? So see if you don't notice something about this square on side A, this square on side B, and the square on side C. Pause and think about that. What you may have noticed is that if you add this to this, the area of the square on side A plus the area of the square on side B, you get the area of the square on side C. That is happening on every one of these right triangles. All right? And what that tells me is that, you know how hard it was to count the area of the tilted square there? We could have just added these 2 numbers together to get that area. Now, the reason why you might want that area is because if you take the square root of the area, you get a side length. So we can actually find the lengths of the triangle. This one's easy because it's not tilted. That one's 3, that one's 4. But we can also get the length of this tilted just by taking the square root of the area, which in this case was 25. So we can figure out this length of the hypotenuse, the long slanted side, if we just know the 2 other sides. Kind of like you can find the area of the triangle if you know the base and the height. Okay, so here is that, here's what we noticed. The areas, the sum of the areas, got to remember that these are areas now, otherwise you'll make mistakes when you use the formula. The sum of the areas on the 2 legs, remember the legs are the sides that make the right angle. The sum of the areas, I should put, of the squares drawn on the legs of the, I'm not going to write all this, but on the sum of the areas of the squares on the legs equals the area of the square drawn on the hypotenuse. Remember, the hypotenuse is the long side. Okay, and that's Pythagorean's theorem. And we're going to find out what you can do with that. So that you write it out like this. In a right triangle, the area of the square built on the hypotenuse of the triangle is equal to the sum of the areas of the squares built on the legs. And you might see it, this is what the formula looks like. A squared plus B squared equals C squared. So A, B, and C are the sides of the triangle. And A squared, B squared, and C squared are the area of the squares drawn on those. So A squared plus B squared will always equal C squared if it's a right triangle. And so let me show you what you can do with that. It's pretty cool. So let's say we know that this tile here is a 6-inch tile, 6-inch square tile. And we're going to cut the diagonal, and we want to know how long that cut is, that C. Well, we know that if I find the area of this square on this leg and add it to the area of the square on this leg, it'll equal the area of the square on this leg. So 6 times 6 is 36. The area of the square on the legs are 36. That means this area of the square on this hypotenuse is 72, which means the length of the side is the square root of 72, which is about 8.5. Okay? So let's do a problem here. If we have a right triangle and the lengths of the legs are 9 and 12, now that would be this side and this side. We want to know the length of the hypotenuse. So what you're going to do is square each of those leg lengths. You're going to do 9 squared plus, let's just call this x for now, this missing one. So 9 squared plus 12 squared, the area of the square on the legs added together equals the area of the square on the hypotenuse, which I labeled as x. So now I'm going to just find out what this equals, add those two together. That's 81 plus 144, which is 225. That's x squared. I got to do one more step. I have to undo this x squared, so I'm going to do the square root to undo that. And the square root of 225 is 15. All right, so x is 15. Now, the one thing students kind of forget to do is this step here. But if you would end up with a side length of 225, you'd go, oh man, that's way too crazy long. It turns out that this side length, this 15, can't be any more than these two numbers added together. So you can kind of use that as a way to guide you. Now, sometimes you might be missing one of the shorter sides. But the theorem works the same, that if I find the area of the squares on the legs, so if I do 5 squared plus b squared, that's got to equal the hypotenuse square, which is 13 squared. And the way you know that is because this is the longest side, so it would have the biggest square. And the two smaller squares drawn on the legs would add up to that one. So, and so now I can just simplify this. 25 plus b squared is equal to 169. And I'm going to take this 25 away from 169. I'm backtracking. So my b squared is going to equal 169 minus 25, which is 144. And then you know now that to get b, you would do the square root of that to undo that squared. So square root of 144 equals 12. So b is 12. All right. So why don't you try this next one? See if you got it. Find a. Now remember, a is going to be smaller than either one of these, so it's going to be like the last problem we did. All right. I should have got 9 for that. There's another property in this Pythagorean's theorem, and that is that if you have 3 numbers, and I'll just give you an example. If you have 3 numbers like 3, 4, and 5, and they're the sides of a triangle, so I'll just draw a triangle. Let's say that side's 3, that side's 4, and that side's 5. If you take the 2 smaller numbers and square them, and they equal the biggest number squared, if this is true, then you know that that triangle is a right triangle. So this is true, isn't it? 9 plus 16 is 25. So 3, 4, and 5 would make, if you make a triangle with side lengths 3, 4, and 5, it will be a right triangle. Okay? So here's the property. So what you're going to do is you're going to do 12 squared plus 16 squared, the 2 smaller sides squared, and add them together and see if they equal 20 squared. If they do, you're going to go ahead and circle equal. If they don't, you're going to say not equal. And if it's not equal, then it's not a right triangle. Okay? So go ahead and try those two. So you should have found that this top one is a right triangle because 12 squared plus 16 squared is equal to 20 squared. And the second one is not a right triangle because 9 squared plus 11 squared is not equal to 14 squared. All right. So let's check these out, you guys, and here's how you're going to check them out. You're going to take, so these are any old triangle, and we want to know if it's a right triangle. So you're going to do 5 squared plus 8 squared and see if that's equal to 10 squared. So this is a question mark here. We don't know yet. So 5 squared is 25. 8 squared is 64. 25 plus 64 is 89. 89 is not equal to 10 squared, which is 100. So it's not equal in that case. So we're going to say, I'll just cross it out. That's a no. Okay, you check the rest of them. All right, the only one I found that worked was B. 9 squared plus 40 squared is equal to 41 squared. That is true. And so if you make a triangle with side lengths 9, 40, and 41, it will be a right triangle. All right. So on this one, you're just going to find which one of these do you think is a right triangle. Just kind of say yes or no on each of them. Oh, actually, there's only one to do. But remember that the two smaller sides have to be the legs. So the one that you would be checking is this one. You would never put the smallest number on the longest side of the triangle, or even the middle-sized one. So we're not checking that. We're checking this, and which means we want to know if this is true. Is 20 squared plus 47 squared equal to 52 squared? Check. Here's what you got when you did those two problems. The equation is false. This is not equal to 52 squared, so it is not a right triangle. All right, I think I'm going to let you go there and work on your assignment, which is on page 26 here, right here. Go ahead and do that, and we'll talk more about this the next time we meet. Good luck.